For those of you who missed week 17, which was the first week back of the second semester, you have missed a lab, and that lab is in your binder. It is Chemlab 8, Modeling Molecular Shapes. And these questions are actually questions that you're going to be answering on week 18. The instructions are here with a place to take some notes, and the sheet behind that in your binder has what you needed to do. So you're given the formulas of various covalently bonded molecules, and you're asked to draw the Lewis dot diagram, have a short description of the molecule, and the description should include things like, is this a polar molecule or not a polar molecule? And that will be based on the polarity of the bond. And I'll explain the difference in a moment. The other thing that you'll be putting in description is this a linear molecule, or does it form a three-dimensional shape? Is it bent? Does it form a little pyramid shape, etc.? The other more complicated shapes that are covered in Chapter 8, Section 4, I am not asking you to actually memorize those or be able to predict them. I simply want you to have the concept that some molecules do indeed have a three-dimensional shape. So the kits look something like this. You have bonds that are represented by these short sticks. These are rigid. And then you have some bonds that are flexible. And that's because when atoms form double and triple bonds, the orbitals are distorted. And the way that the model shows you that distortion is by bending the bonds like this. And so we have the black atom that usually represents carbon. It has 4 different holes. We then have either nitrogen or phosphorus that is in group 15. And so it has 3 available bonding sites most of the time. And then we have oxygen, which is red, is in group 16. It has 2 possible bonding sites. And then we have the white ones are hydrogen. They only have 1 possible bonding site. We have a few of those. Okay. And then we also have atoms from group 17. And those are the halogen group. They only have 1 bonding site. The difference between the hydrogen and the halogen is, of course, that the hydrogen has only 1 electron in its valence shell. The halogen group, fluorine, chlorine, etc., have 7 electrons in their valence shell. So I'm going to put them here. And the first molecule that you're asked to put together is hydrogen. And so we take 1 hydrogen atom and another hydrogen atom, and we're going to take one of these rigid bonds, and that's it. You have a molecule of hydrogen. And hydrogen is one of the diatomic atoms, or elements, So elements like hydrogen, oxygen, nitrogen, and all of the elements in group 17 always travel in nature as pairs. And so this is elemental hydrogen. This is how it travels in nature. This is oxygen. This is how it travels in nature. This is nitrogen. This is how it travels in nature. And so you're then asked to do the Lewis dot diagram, and it is a single bond. Each of the atoms has 1 electron. And so in this bond, 2 electrons are shared, which is true of every single bond. The description of this bond, this is a linear bond. It is not really in 3 dimensions, okay? And because both of the atoms are hydrogen, the difference in electronegativity is going to be 0 because the electronegativity of hydrogen minus the electronegativity of hydrogen is going to be 0. All right, and so the polarity is also going to be 0. The bond is not polar and the molecule is not polar. Let's take a look at oxygen. So now we have oxygen. We need 2 atoms of oxygen. There's 2 possible bonding sites. And so we could grab one of these rigid bonds, but the minute you do that, you're going to realize that you're going to leave a bonding site with an unpaired electron. That is not going to work. And so for oxygen, we need to use our flexible bonds. I'm going to put one on each side of this oxygen atom, and then I'm going to plug it into both sides of the other atoms. And lo and behold, I have a double bond. There are 2 pairs of electrons being shared by the oxygen atoms. Okay, 2 pairs, a total of 4 electrons. So my description of this particular molecule is, again, I have a linear molecule. My polarity, again, for the same reasons of hydrogen, my polarity is going to be non-polar. So the bond is non-polar and the molecule is non-polar. Let's go down to nitrogen. So in nitrogen, I have 3 possible bonding sites, and I'm going to need another nitrogen atom. There we go. Okay, so I have, and this is a slightly different one. Let me get one from this kit we're using currently. There we go. So I have 2 nitrogen atoms. They each have 3 bonding sites. And so how am I going to bond them together? Well, it sounds like I'm going to need a triple bond, and I do. So I take my flexible bonds. I'm going to take 3 of them like this, and then I'm going to plug them in to the other atom. And you're even going to feel, oh, wow, this is going to take a lot of distortion. Notice that these bonds are more distorted than the double bonds, okay? And if you take a look at the tables in your textbook, you will realize that as I go from a single bond to a double bond to a triple bond, indeed, the nuclei get closer together, and the energy necessary to break the bonds increases. So it takes more energy to break a double bond than a single bond. And it takes more energy to break a triple bond from a double bond. Again, I think that's kind of intuitive. All right, same thing here. This is a linear molecule. The bonds are going to be non-polar bonds because the difference in an electronegativity is going to be 0. And so my bond is also going to be, my molecule is also going to be non-polar. Let's do water. To do that, I'm going to have to undo the molecules I've already done so that I can use these atoms again. Okay, and so I have H2O. I'm going to need 2 hydrogens, and I'm going to need 1 oxygen. All right, and so this is fairly easy to see. Okay, I have, actually, I'm not going to use this one. I'm going to use this one, the rigid bond. Okay, so here I have 2 rigid bonds, and I bond the hydrogen to the oxygen like this. And you notice right away that, wow, what the model is showing you here is that this is not a linear molecule. This is a bent molecule. And the degrees, the angle of the degrees here is actually a little bit over 105. So this is now going to have meaning for describing this particular molecule. So you're going to do the Lewis dot diagram here, okay? There is a single bond between the hydrogen and the oxygen, and another single bond between this hydrogen and the oxygen. Wherever you have hydrogens, you're can only make single bonds because hydrogens can only make one bond. When I describe this molecule, well, the first thing I have to do is over here in polarity, I have got to find the difference between the electronegativity of oxygen and the electronegativity of hydrogen. And what we're going to find is that that number is going to indicate this is a polar bond. So I have two polar bonds here, and the molecule is not symmetrical. So I have oxygen on one side and I have the hydrogens on another side. So in this case, this is going to be a polar molecule. The oxygen side is going to be slightly negative and the hydrogen side is going to be slightly positive. For those of you who had biology with me, you know that this polarity of the water molecule is what enables the water molecule to produce hydrogen bonds. And this is why water has all of its special characteristics and why water makes life possible on planet Earth. Okay, so you'll go on to do all the rest of these, find the numbers for yourselves. Okay, next we're going to take phosphorus. Phosphorus is also in group 15, so I'm going to need to undo this nitrogen because it's going to have the exact same bonding pattern as nitrogen because nitrogen and phosphorus are in the same group. So in this case, okay, I have phosphorus that's going to be in the middle. And I have 3 bonding sites, and I'm going to pull my little rigid ones out, and I'm going to add my hydrogen into each of these bonding sites. Okay, and now you'll notice I do not have a linear molecule. This is not linear, okay? And this is also not symmetrical because the phosphorus, you'll notice, is above the plane of the hydrogens. So this is not symmetrical. So now what I need to do is I need to, again, find the difference in electronegativity between the phosphorus and the hydrogen. And I need to find, is that going to be a mostly ionic bond? Well, it's not because this is going to be a covalent bond. Is it going to be polar covalent? Is it going to be mostly covalent? Is it going to be covalent? That is what you need to find, or non-polar covalent. And so in this case, if these bonds are polar bonds, okay, we are going to have a polar molecule because this side is going to be negative and the hydrogens are going to be positive. But you need to find that out by calculating the difference in electronegativity here. Let's do the rest of the molecules quickly, and then you can do that. Okay, so now I'm going to make a carbon molecule. Carbon, of course, has 4 bonding sites. Okay, and so I'm going to move my covalent bonds here. So here I have my 4 covalent bonds that are going to go on to the carbon. Remember, carbon is the king of covalent bonding. And so I'm going to put those in here. And I'm going to put fluorines. So this is going to be carbon tetrafluoride. Okay, and so I'm going to get my green fluorine molecules, and I'm going to put, remember, this is, we talked about this in chapter 1 because this happens to be one of the CFFs that we were reading about at that time. Okay, so here I have a carbon tetrafluoride. Okay, and you're going to do the Lewis dot diagram. And of course, the Lewis dot diagram is going to look flat, right? The Lewis dot diagram on something like this is going to look like a cross, okay? Because that just shows the general structure. But in the description, aha, this is some kind of a tetrahedron, okay, because there are 4 angles to this. All right, so this does have a, three-dimensional shape. When you take a look at the polarity, okay, you are going to find that each of these is indeed a polar bond because fluorine has a very high electronegativity, much higher than carbon. However, if you can see how this molecule is built, you realize that this molecule is symmetrical. The positive charges of the hydrogen are completely evenly distributed around this carbon atom. And so this molecule, which is this perfect tetrahedral molecule, okay, this molecule, even though it has polar bonds, this molecule is non-polar. Okay, so now let's go to carbon dioxide. All right, so I have carbon and I have 2 oxygens. Now, I can make 2 bonds with each of my oxygens, and carbon, you'll remember, can make 4 bonds. But the only way for oxygen to have 2 bonds with carbon and this other oxygen to also have 2 bonds with carbon means that this molecule is going to come together with double bonds. So I'm going to put 2 bonds on this oxygen, and I'm going to attach it like this. And you'll see that there is only one way that this fits. This is why this is called a chemistry molecular model shape, because it automatically forms the shapes that we want in our atoms, between our atoms and in our molecules. So here we have carbon dioxide. All right, and so again, here we do have a linear molecule. This is a line, okay? And then again, try to figure out the polarity. Are these bonds polar bonds? Okay, and so we subtract the electronegativity of carbon from the electronegativity of oxygen and find what it is. Now, in this case, we again have symmetry. And because of that, even if the bond is a polar bond, the molecule is not going to be a polar molecule, because the atom that's on one side is also on the other side, and whatever the opposite charge is, it's evenly distributed around the center atom. So this is a non-polar molecule, even if you find that this is a polar bond. Do the math and find out. The next thing we're going to do is this molecule, which is can have several names. Okay, so you can call this hydrogen carbon nitride. Okay, however, CN has an old name that's been used for a long time, and so we call this hydrogen cyanide. All right, so what I need is I'm going to need a oxygen atom, and I'm going to need a carbon atom, and I'm going to need a nitrogen atom. Okay, so we're going to start with the hydrogen first. We know that hydrogen can only make 1 bond, so I'm going to pop it into the carbon. And now I have 1, 2, 3 bonds left. Well, that's great, because I only have 3 bonds in the nitrogen. And so these are going to be triple bonds. So I'm going to take my triple bonds here and pop them in here. And now I'm going to pop them into the carbon. Okay, so this is going to be my bond. So again, notice I'm going to describe this as a linear, this is a linear molecule. Okay, the atoms form a nice little line. I'm going to do the Lewis dot diagrams, or you are going to do it. Okay, and now we got to figure out, is this going to be a polar molecule or not? Well, I need to find the difference in electronegativity between carbon and nitrogen. And I then need to find the electronegativity difference between carbon and hydrogen. And when you do this, you're going to find that these bonds do not have the exact same qualities. And so I want you to think about, okay, based on what you find in electronegativity, do you think this is going to be polar or nonpolar? Notice that we don't have exact symmetry here because this atom is not the same as this atom. So think about that when you put it together, okay? And then finally, we have carbon dioxide. Well, I'm going to tell you right now, before you even start doing this on your own, that carbon dioxide is an exception. You have already read about exceptions to the octet, and this is one of them, okay? And unfortunately, because of this, all right, we actually cannot use the VSEPR models to show us this type of molecule, because this is going to be a coordinate covalent bond. So here I have my carbon, and here I have one oxygen. And I have 4 bonding sites here, but I only have 2 here. Well, what that's going to mean is that in order for these to join, I am going to have to do something funky with my bonds. And this is what happens, okay? Remember that in carbon dioxide, each atom of oxygen has two covalent bonds with carbon. But right here, I don't have any room for any more covalent bonds on hydrogen. And there are 2 unpaired electrons here represented by the holes on carbon. And so what occurs in making this particular molecule is that I need to work with the remaining electrons around oxygen. You'll remember that oxygen has 6 valence electrons. 4 of those electrons are in pairs. So here I have shared electrons, and then I have 2 pairs that are still surrounding the oxygen atom. And so what occurs in carbon monoxide is that these 2 electrons pair up on the opposite side to oxygen. And then the oxygen makes another bond. It actually makes a triple bond with carbon. And it leaves 1 pair of electrons over here. So oxygen contributes 2 electrons to be shared between the carbon and the atom, the oxygen atom. So when an atom does that, when an atom contributes 2 electrons to share, that is called a coordinate covalent bond. I only want you to be able to recognize things like an expanded quartet, a coordinate covalent bond, and an incomplete octet. I would not ask you to do a Lewis dot diagram for those on a test. Here you can, because number 1, you can look it up, and you can figure out if this molecule is going to be polar or not. I think you have some information here that can tell you whether that's going to be the case or not. All right. In general, linear bonds are often not polar. I can think of a couple examples, but go figure out the electronegativity difference and then decide, is this atom going to be polar or not? So this is Chemlab 8. The other parts of Chemlab of labs for Chapter 8. Most students will be able to make them up when they return week 18. See you then.